Nwacc, Survey of the Universe, Lecture 24, Life in the Universe, for Monday, April 27th, 2020. Exam 4 is posted to Canvas. It is due May 1st. It is different than previous exams. Rather than doing multiple choice, you're going to do citizen science. You're going to make a contribution to astronomy research at Galaxy Zoo. So here it is. Doop-de-doo. Exam 4. And here are the instructions down here. The material from lectures 19 through 24, that is up to and including today, will still appear on the comprehensive final. So, to make it easier to study for the final, I've added a folder in the Files section of Canvas called Study Material for Comprehensive Final, which includes exams 1, 2, and 3, and also a previous semester's version of exam 4. So the final exam will be multiple choice, and the questions will be over the same topics, though not necessarily the same questions, as exams 1 through 3 and the previous semester's version of exam 4. So use those exams to study for the final. So we begin now, as we usually do, with poetry. Say it with me. Dark matter is invisible gravity. It pulls together galaxies. Dark energy is like anti-gravity, pushing the cosmos apart since the very start. When I say astronomy, you say rocks. Astronomy! Did you say it? Yeah, you did. Well, let's talk about life and the potential for life outside of Earth. Before we do that, we have to talk a little bit about life on Earth. I'll caution you, I am not a biologist, so I know the basics, but you can learn more from a biology class than you can from here. So what we know about the history of life on Earth comes from the fossil record. That is either the remnants of organisms or the imprints that organisms left in rocks that have been buried underground. And the deeper underground a layer of fossils is, the farther back in time that those fossils are. Because era after era, new layers get added to the ground. So according to the evidence, life on Earth appeared very quickly after the period of heavy bombardment ended. That is, after the giant comets and asteroids, the planetesimals, stopped smashing into Earth. After Earth, being a full-blown planet, had already vacuumed up the planetesimals, the giant comets and asteroids, from this region of the solar system. Once that happened, once there were no longer giant comets and asteroids smashing into the planet every single day, things became calm enough for life to form. This began probably about 3.85 billion years ago. So when we look at the fossil record, it is a story told in layers, because year after year, century after century, 1,000 years after 1,000 years, million years after million years, layers are added to the ground. The closer to the surface you get, the more recent the layer. The deeper you go, the farther back in time you go. So the layers themselves tell us the relative ages of the fossil. We know that the fossils down below are older than the fossils up above. That doesn't tell us absolute ages, right? Just because you know that one fossil is older than the other doesn't mean you know either of their ages. We get the actual ages, the absolute ages, from radiometric dating. If you get a chance to go to Arizona, please, at some point in your life, make the road trip out to the Grand Canyon. It is worth it. Beautiful, beautiful canyon that was carved out by the Colorado River, which flows from the Rocky Mountains, which is high up and therefore has a lot of gravitational potential energy. And then as it flows downward, that gravitational potential energy is converted to kinetic energy. So by the time the Colorado River reaches the Grand Canyon, it's moving very fast and therefore is to this day carving rock out of the ground. And the Grand Canyon, in the Grand Canyon, you can see the layers dating back 500 million years. So the number that I quoted, 3.85 billion years ago for the start of life on Earth, comes from carbon isotope evidence. Boy, that sounds funny, doesn't it? I don't know that much about carbon isotope evidence, so I'm just going to leave it there. In physics, we call that a hand-waving argument. I'm just repeating what's in your book. I do understand fossils a little bit, so I'll talk more about those. The oldest fossils are bacteria-like organisms, and those date back to about 3.5 billion years ago. This is a timeline of Earth. Here is the first life, 3.85 billion years ago. For about half of Earth's history, the only life on Earth were single-celled organisms. So when we look for life on other planets, we're not necessarily looking for alien civilizations, though that would be nice. It'd be great to meet little green men or whatever. But most likely what we're going to find are single-celled organisms, because for the first half of Earth's history, that is all that was here. And even to this day, single-celled organisms dominate this planet. There are more bacteria in and on your body than there are people on the Earth. You are an entire planet for single-celled organisms. So once oxygen began to build up, for the first organisms on Earth found oxygen to be toxic. It was their poop. And so oxygen built up and built up and built up, and then life had to adapt. It had to evolve so that it could use oxygen instead of dying from it. And once that happened, life became a lot more plentiful. There were a whole lot more variety of life. Evolution was able to do its job. Dinosaurs and tiny little mammals appeared only 200 million years ago. That's very recent compared to the entire timeline of the Earth. Dinosaurs dominated the land and the water for a couple 100 million years, or 150 million years, up until about 70 million years ago, 68, when a giant comet, it looks like, smashed into the Yucatan Peninsula, creating a dust cloud that surrounded the Earth and created a wintertime. It blocked out the sun, and the dinosaurs, most of them, died. They weren't able to survive the cold temperatures. The ones that remained turned into birds. Birds are just dinosaurs. They're just leftover dinosaurs. And the little mammals, however, had fur. And guess what? Fur is pretty good for cold weather, so mammals then were able to take the place of dinosaurs as the dominant creatures of the land. So mammals were prominent, have been prominent for the past 68 million years. Humans, however, did not show up till a few 100,000 years ago. Humans are very recent. We just now got here. For some reason, this is a controversial statement among people who are not scientists, but it's not controversial at all among people who are. Life evolves. We know that by looking at the fossil record. Remember, as you go deeper into the Earth, you get older and older fossils. And what we find is, as you go farther back in time, species converge. The fossils start to look more and more alike until they are, in fact, the same species. And then as you go deeper and deeper into the fossil, deeper and deeper back in time, more and more species converge. So what this tells us is that species change with time and they split off from one another. So this is the theory of evolution. It was first formulated by Charles Darwin in the 19th century. And while the basic idea that species evolve and change and adapt over time is correct, the specific mechanisms that he posited for that turned out to be wrong, as is often the case. A brand new theory often gets the details wrong, but it takes 150 years of added research to get the details right. So Darwin's big idea was right, although 150 years of research has upgraded and improved the theory, the details of the theory. What the fossil record tells us is that species come from a common ancestor. As you go back in time, species converge, which means as you go forward in time, species diverge. They split off. It may be that the earliest life happened near the bottom of the ocean, near the black smokers. These are volcanic vents deep inside the ocean. And if that's true, that's great news, because Jupiter's moon Europa has shown evidence for having black smokers much like the ones deep in Earth's ocean. So Europa may be a cradle of evolutionary life. Maybe not, we don't know. So it might be that life began in the oceans. It might be, maybe, now we're getting speculative here, that life came to Earth from somewhere else. We do know that we have rocks from the moon here on Earth. We have rocks from Venus and from Mars. The reason this happened is because sometimes if a big comet or asteroid smashes into a planet, it splatters rocks out into space, ejecta, they call it. And those rocks can sometimes, occasionally, make their way to a neighboring planet. We also know that there are organisms here on Earth that can survive space travel at least for a few weeks. That much is experimentally confirmed. Tardigrades, these cute little water bears, have been found to survive in the vacuum of space for a couple of weeks. They did this on the International Space Station. They had 3 samples of tardigrades. One was in the vacuum of space facing the sun. One was in the vacuum of space opposite the sun in shade. And then one was inside the space station as a control. So they knew that one was going to survive. So of course the population inside the space station had no problem. The one facing the sun, most of them died because of ultraviolet radiation. But the one in the cold darkness of space, the population of tardigrades in the cold darkness and vacuum of space, facing away from the sun, not only survived, they reproduced. They're doing fine. So tardigrades can live in extremely harsh conditions for a very long time. And there are other animals, or other organisms, I should say, that can do this. We collectively refer to them as extremophiles. Now, could they survive a trip from Earth to Mars or Mars to Earth? We don't know that. When it comes to organisms' ability to survive long-term in the cold harshness of space, we simply don't know. So to recap, life began about 3.8 billion years ago. Oxygen began forming in our atmosphere 3.5 billion years ago. That oxygen came from life, from cyanobacteria. By about 2 billion years ago, those cyanobacteria were pooping oxygen all up into the atmosphere. And then once life evolved to where it could use oxygen instead of dying from it, poosh, the Cambrian explosion happened. Lots and lots and lots of different species were to evolve then. The earliest human-like creatures happened a few million years ago, the hominids, and human beings came about a few 100,000 years ago. So that's what we know about life on Earth. Does that mean there's life in space on other planets? Not necessarily. However, it's a hand-waving argument, but it's rare in astronomy that we see anything that has been proven to be unique. In fact, I can't think of an example. The sun is not the only star. There are countless stars. Earth is not the only planet. There are countless planets. There are countless comets, countless asteroids, countless galaxies, countless black holes. Everything that we've been able to see in space, if we can look far away and detect whether it's there or not, it's there. When something happens in the universe, it doesn't usually happen once. It happens countless times. Does that mean there are countless biospheres throughout the universe? We don't know. We haven't detected any biospheres except Earth. Earth is the only life that we know about so far. But it might be that the universe does, in fact, have countless biospheres. So what are the necessities of life? Sometimes I get the very valid question, how do we even know what to look for? Maybe life, an alien life, is so different from life on Earth that we wouldn't even know how to detect it. Maybe it's made of completely different chemistry. Maybe it's made of a completely different kind of matter that we don't know about. That's valid. That's true. However, scientists are biased by what we can measure, and what we can measure are the necessities of life on Earth. Biological life. Bags of water. That's what you are. A bag of water. And so that's what we look for. We look for other planets where bags of water could survive. So biological life as we know it, bags of water, need a source of nutrients, that is something to build your body with, to build your organs with, the raw materials to build things with. We need energy so that we can build things and move around. And we need liquid water in order to move the nutrients around. So in your body, liquid water is mostly in the form of blood, but there's also other forms of water in there as well. Liquid water is kind of hard to find, but it's certainly not unique to Earth. Water, H2O, is extremely common in the universe. Don't ever let them tell you water is rare. If someone tells you water is rare in the universe, they absolutely are full of it. They have no idea what they're talking about, and that doesn't stop them from talking. What is kind of rare is liquid water, because remember, it takes two things for water to be liquid. One, you need the right temperature, somewhere between freezing and boiling, and those two temperatures depend on on pressure. And that's the second thing you need, pressure. Here on Earth, we have liquid water oceans because we have a moderate temperature and a glorious atmosphere that provides the pressure to keep the water liquid. Inside of Europa and Jupiter's moon Europa and Saturn's moon Enceladus, there is liquid water. The pressure is provided by the weight of the ice pressing down on the ocean. But on Mars, there's not enough atmosphere to allow pressure enough for water to be liquid, at least above ground. It's not that Mars never gets warm enough. Oh, it can get to 80 degrees Fahrenheit on a good hot summer day on the Martian equator. That has been measured. But even at 80 degrees Fahrenheit, water's not going to be liquid if there's no pressure to keep it liquid. Water is only stable if you have the right temperature and pressure. So, life arose on Earth about almost 4 billion years ago, shortly after heavy bombardment, after the planetesimals stopped smashing into Earth. And life evolved. It changes with time. And I have purposefully neglected to talk about the details of how that happens because I'm not a biologist. But I strongly recommend, if you're interested in this topic, to take a biology class. And if you're still interested, take an evolutionary biology class, which is advanced. But life as we know it, biological life, bags of water, need nutrients, energy, and water. So let's look at life in the solar system. Could there be life on Mars? Well, there's not enough pressure to keep water liquid on the surface, but underground there is, and maybe there's some liquid water pockets underground Mars. What about Europa? There's lots of liquid water under the surface of Europa, and there's energy sources too. Are there nutrients? Let's talk about Mars. We do know, we have compelling evidence that Mars had liquid water in the distant past. We see dry riverbeds. We see rounded pebbles, which suggests that something sanded those pebbles down, like a flowing river. Remember, if you go down to the creek here in Fayetteville or in Bentonville, you'll see rounded pebbles because the water sands the pebbles down. We also see minerals on Mars that are only formed underwater. So that is compelling evidence that there was liquid water on the surface in the past. We also directly detect subsurface ice on Mars and maybe some underground liquid water as well. So that's something. We have rovers wandering around on Mars that look in detail at the rocks. They're actually looking for evidence of fossils. They haven't found any. The Curiosity rover has been hanging around on Mars since 2012, looking for minerals, looking for dry riverbeds. So the answer for Mars is we don't know. There may have been life in the distant past. We haven't found direct evidence of it, but we know there was liquid water. Well, what about Europa or the other moons of Jupiter? Well, there is an underground liquid water ocean underneath Europa. And Ganymede also seems to have a lot of water underneath it as well. Moreover, there is evidence that there are hydrogen vents underground in Europa that could provide an energy source for single-celled organisms. And maybe that means there are stuff hanging up down there. Maybe there are single-celled organisms, maybe even complex things like squids. I don't know. It would be very nice to drill a hole in the ice, send a submarine down there and take pictures. But that would take a whole lot of engineering difficulty. Because remember, Europa is constantly being stretched by Jupiter. So if you were to drill a hole down the ice, you'd have to get several miles down there, and suddenly the whole ice could smash together and destroy your drill. So we don't know how to do that, but NASA is proposing such a mission, so stay tuned. Saturn's moon Titan has lots of organic molecules, natural gas, and other organic molecules. Its surface is too cold for water, but maybe underground? I don't know. That's a common theme when it comes to life outside Earth. I don't know. Saturn's moon Enceladus. Lots and lots and lots and lots and lots of water underground in Enceladus. I told you before that they found hydrogen vents under Europa. I may have been thinking about Enceladus. I apologize for that. That may not be true with Europa. It may only be true with Enceladus. Nevertheless, hydrogen vents, which could be a source of energy. So, Mars had liquid water in the past. Does that mean it had life? The several moons of Jupiter and Saturn have have liquid water underground. Does that mean there's life under there? Well, if we don't know about life in the solar system, imagine how much we don't know about life around other stars. But let's start with what we think we know, or at least what we're looking for. What we're looking for is the habitability zone. This is the zone around a star that, if a planet has the right atmosphere, could be the right temperature for liquid water, or would be the right temperature for water to be liquid. So, for example, Earth is in the habitability zone around the sun. Mars is kind of on the edge, meaning if Mars had a thicker atmosphere, it could have liquid water. However, there is an issue with Mars. In order for Mars to be warm enough to have lots of liquid water, it would need lots of carbon dioxide, maybe enough that it would be toxic to life as we know it. But again, this is a very speculative science, so it's a lot of intuition and also some experiments to back it up. The Arkansas Center for Space and Planetary Sciences at the University of Arkansas and UALR do experiments trying to recreate the conditions on Mars and see if they can make water flow, make water be liquid. The brighter a star is, the larger its habitable zone will be, and the farther away from the star it will be. And I want to separate these two concepts here. It's not the hotter the star is. Temperature of the star is not important. It is the luminosity of the star that is important. Why is that? We don't get heat from the sun. We don't. We get light from the sun. And that light, that radiant energy, is transformed into thermal energy when the light strikes the air, the ground, and especially the ocean. So it is not the temperature of the star that counts. It is the luminosity of the star. And those two things are related, but they're not the same thing. So we say that a world is habitable if it contains the necessities for life as we know it, like liquid water. That doesn't mean it's inhabited. That doesn't mean it has life. So things we think are required for habitability, for liquid water to happen and for life to form. You have to be the right distance from the center of the galaxy. All we have is computer models to tell us this, so this story may change in a few years. But if your star is too close to the center of the galaxy, you have problems. First off, stars are too close together, which means they're throwing comets at each other the whole time. So you don't want to live on a planet that's being bombarded with comets. That could be bad for your civilization or even for your biosphere. Second, if you're too close to the center of the galaxy, you might have to deal with supernovae, stars exploding all the time. Boy, that would be bad for life if the next door neighbor's star suddenly exploded. Oops. And a third thing is if you're really close to the center of the galaxy, you've got to deal with radiation from the magnetic field and the accretion disk of the supermassive black hole at the center of the galaxy, Sagittarius A star. So you don't want to be too close to the center of the galaxy. There's lots of extinction events, as we call them, that go on in the center of the galaxy. On the other hand, you don't want to be too far away from the center of the galaxy. You don't want to be at the very edge of the galaxy either, because out there, we think, there's not enough supernova to create iron and nickel that form the core of a rocky planet like Earth. There's simply not enough heavy elements at the edge of the galaxy to form rocky planets. So here on Earth, our sun is in the suburbs. We're not too close to the center of the galaxy so that there are extinction events happening all the time. But we're just close enough to the center that there are enough supernova around to create the heavy elements so that we can have a rocky planet to stand on, but not so many supernova that life gets wiped out as soon as it's formed. In addition to being the proper distance from the center of the galaxy, you also need to be the right distance from your star, which means not too hot, not too cold, right? If it's too hot, your oceans are going to boil off. If it's too cold, your oceans are going to freeze. You got to have oceans, you got to have water so that it can be liquid. You got to have the right atmosphere so that it can be liquid. You need volcanoes to replenish your atmosphere, and you need oceans to absorb the carbon dioxide from the volcanoes. So volcanoes replenish the carbon dioxide, oceans absorb the carbon dioxide. Together, oceans and volcanoes make a thermostat to prevent your planet from getting too hot or too cold for too long a time. Now that doesn't mean the ocean volcano thermostat is going to save humans from human-induced global warming. It will take hundreds of thousands or millions of years for the oceans to absorb all of the carbon dioxide we've put into the atmosphere. So it will. Don't worry about saving Earth. Earth will be fine. The biosphere will recover. Earth is not fragile. Humans are fragile. Save the humans. Stop putting carbon dioxide in the atmosphere. If you want volcanoes, it helps to have plate tectonics. That is, you have continental plates rubbing against each other, melting the rock and spewing them out in the form of volcanoes. And it helps to have a magnetic field in your planet to protect your atmosphere from your star's radiation. If not for our magnetic field, the sun's radiation would pick the atmosphere off one molecule at a time until there was nothing left. We think that's what happened to Mars. Once its core cooled, its magnetic field dropped to almost nothing, and it no longer had any protection from the sun's radiation. So the sun's radiation picked away at its atmosphere. Its volcanoes, once the core cooled off, stopped replenishing the atmosphere, and Mars is so small it didn't have much gravity to hold on to it anyway. So those three things caused Mars's atmosphere to disappear. So we think you want a big planet like Earth, so that it has a molten core, so that it can produce volcanoes and a magnetic field. But this is kind of a biased view, right? I mean, what we're really saying is because life as we know it exists on Earth, and that's the only data point we have, we think what we want is another planet that's as much like Earth as possible. So that's what we're looking for. Could there be a completely different kind of planet where life is also evolved? Maybe. We just don't have any data on that. So right now, exobiologists, people looking for life on other planets, are looking for conditions on those planets that more or less match the conditions on Earth. You kind of want a massive star. Our sun is a low mass star, but it's by no means the lowest mass. When it comes to mass, our sun is like an upper middle class person in the United States. Say you're a doctor or a lawyer in the United States. If you're a doctor or a lawyer in the United States, you probably have more money than most people in the world. But you've got nothing compared to the billionaires of the world. Likewise, our sun has more mass than most stars in the universe. But our sun has nothing compared to the most massive stars. So we look for stars that are about the mass of our sun, so that they have large habitable zones, lots of space that planets can have life. And also, we want the habitable zone to be far away from the star, because if the habitable zone is too close to the star, then the star's radiation could zap life. So for example, this star over here, a little red dwarf star, 1/10 the mass of the sun, there are lots of those around. Most stars in the universe are tiny little red dwarf stars, and their habitable zones are really close to the stars. problem is little red dwarf stars have a lot of stellar flares. They have strong magnetic fields, and so they throw plasma like a whip at those planets that are in the habitable zone. So, at least based on what we know of life on Earth, it's not likely life could survive on those planets because they're too close to the star. The star is zapping the planets with radiation all the time and with plasma. So we want a big star, a fairly massive star. Our sun's mass may be a little bigger. As far as planets go, we want a big planet like Earth. Again, we're biased because Earth works. Earth has life, so everything we know about life says life does really well on Earth. So we're looking for Earth-like planets. If a planet is too small, like Mars, then its core is going to cool off pretty quickly in geologic time after a few billion years. And once the core cools off, you no longer have internal heat to drive volcanoes to replenish the atmosphere. You also, once the core cools off, lose your magnetic field, so the radiation from your star destroys your atmosphere. And of course, you don't have much gravity to hold on to the atmosphere. So we want a big planet so that we can maintain an atmosphere. So we're looking for planets where other life might exist. The Kepler spacecraft monitored 150,000 stars. I put 100,000 here. I think the correct number is 150. They found 30 Earth-like planets. These numbers are old. You should go back to the previous lecture where we talked about exoplanets. The Kepler's found dozens, we'll say, of Earth-like planets in habitable zones of nearby stars. Though caveat, most of those are around red dwarf stars, so we don't think life could actually survive there. But again, we could be surprised. In fact, in 2016, our next door neighbor star, Proxima Centauri, the European Southern Observatory found a planet in its habitable zone. But Proxima Centauri is a little bitty red dwarf star, which means the planet in the habitable zone is really close to the star. And in fact, the next year in 2017, Proxima Centauri put out a stellar flare that would have just destroyed any life on that planet. So what about the galaxy? Here is what we think is the habitable zone of a galaxy. And again, we only have computer models for this. If you're too close to the center, you've got supernova as an extinction event, lots and lots of supernovae. You've got stars that are really close together, which means they're going to throw comets at each other. So that could be an extinction event. The sort of a giant comet hit the Earth and killed all the dinosaurs. And if that were to happen every few thousand years, then it would be really hard for life to flourish here. It would be really hard for civilizations to flourish. Maybe the biosphere would recover. But human-like creatures, probably not. And also, there's a lot of radiation in this part of the galaxy. This is where we live, or this is at least an analog to where we live. We don't live in the galaxy pictured here. We live in the Milky Way, of course. Out here, we think, at the rim of the galaxy, there's just not enough heavy elements to make rocky planets. Not enough iron and nickel, because there are not enough supernova to make iron and nickel. Remember, it is supernova that manufacture the iron and nickel that form the core of Earth. And it might be that Jupiter and our moon have also helped life evolve. We certainly know the moon has affected life in things like tides, but it also may be that because we have a giant moon, the gravity from our moon is keeping the Earth's axis stable. Earth's axis is tilted 23.5 degrees, and as far as we can tell, that doesn't change over time. Computer models tell us that without the moon, the Earth's axis tilt would vary wildly over the course of a few million years. We think Mars is doing that. That would lead to huge changes in the climate every few million years. And it might be hard for life to evolve when the climate changes drastically. Imagine what a polar bear would do if its habitat suddenly became a rainforest. Imagine what an alligator would do if its habitat suddenly became the North Pole, like the North Pole. You would have a lot of extinctions if the Earth's axis were to chaotically tilt up and down. But it doesn't, and we think the reason it doesn't do that is because of the gravity of the moon. So it might be that a large moon is necessary for life to evolve on a rocky planet, and we simply don't know how common large moons are around rocky planets. Right now, we can detect some rocky planets around neighboring stars, but we can't really see their moons, so we don't know if they have any. Jupiter, we think, also protects us from the sorts of comets that killed the dinosaurs. If a comet gets too close to Jupiter, Jupiter kicks it right out into the Oort cloud. Jupiter is a vacuum cleaner. Jupiter protects us. You might think of it as a goalie. It kicks the soccer balls right out of the solar system, right out into the Oort cloud, so that they don't smash into Earth nearly as often as they would. We think that the sort of comets that smashed into the Earth and killed the dinosaurs would be a lot more common, if not for Jupiter. So it might be that a Jupiter-like planet is necessary for life to evolve. Now, the good news is that Jupiter-like planets appear to be very common. So while we don't know if Earth's moon is common or not, we do know that Jupiter-like planets are very common, at least in this part of the galaxy. So it might be that a moon and a Jupiter-like planet, a large moon and a Jupiter-like planet are necessary for evolution. It might not be. It might be that even without these influences, life could find a way to evolve. We don't know. We only have one data point, Earth. So the bottom line is, we don't know. So to recap, we think that life, in order to evolve, requires the right distance from your star, the right distance from the center of the galaxy. So from the star, not too hot, not too cold. From the center of the galaxy, not too many extinction events, but enough rock to form planets. You need a big world so that it has volcanoes, plate tectonics, and a magnetic field, because it has a molten core. And is life rare or common? We don't know. But we do think that there are lots and lots and lots and lots and lots of Earth-like planets out there. We have detected lots of rocky planets about the size of Earth orbiting stars that are like our sun. Or we detected enough of them that we run statistics, and the statistics tell us there are probably millions of Earth-like planets in our galaxy. Does that mean they all have life? So from the 1960s up until 2020, the search for extraterrestrial intelligence, SETI, was active. In fact, SETI might be active, but SETI at home is not. Up until this year, you could use your computer to look for alien civilizations, but they stopped that program, sadly. No one found any, sadly. So, how many civilizations are there? 0? Well, that's not true. There's one. There's Earth. Are we the only one? Are there 10 civilizations in our galaxy? 100? 1,000? 1,000,000? And what about outside our galaxy? Remember, there are a few 100 billion stars in our galaxy, and a few 100 billion galaxies between here and the cosmic microwave background. That is 10 to the 22 stars just within reach of our telescopes. Not that we can see each of those stars. That's an estimate, not a count. Nonetheless, it's a big freaking number. I don't know about you, but I would be shocked if I were suddenly to be plugged into all the knowledge of the universe and find that Earth is the only planet out of 10 to the 22 stars that had life, or even that had a civilization. And remember, 10 to the 22 stars, that's just between here and the cosmic microwave background. That's just between here and the observed. That's just in the observable universe, in the observed universe. The global universe, that is everything that actually exists, may be much, 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 much bigger than that. In fact, we have some evidence to suggest that it is, though we can't see that far. So how do we even talk about it? The way that we talk about it is through something we call the Drake equation. The Drake equation is not a law of physics like the law of gravity, right? This is simply a way to parameterize our ignorance. That is, to put a number, guesses, into numbers that we simply don't know. And then you multiply those numbers together, and that tells you, assuming your guesses are correct, how many civilizations there should be in our galaxy. The way that I have the Drake equation formulated here, it only talks about our Milky Way galaxy. But, multiply everything by 100 billion if you want to talk about other galaxies. All right, so what this says is that the total number of civilizations in our Milky Way galaxies is the total number of habitable planets, which there appear to be millions, times the fraction of those planets where life has evolved. Now, we have no idea what that fraction is, somewhere between 0 and 1. And of all the planets that have life, this number here, F-civ, is the fraction of those where life evolves civilizations. Remember, Earth did not evolve a civilization until 6,000 years ago, assuming you define civilization as being agriculture. That's 6,000 or 8,000 years. Earth is 4.5 billion years old. So for the vast majority of Earth's history, Earth did not have civilizations, as far as we can tell. Nevertheless, some fraction of planets where life evolves eventually evolve civilizations. We don't know what fraction that is. Somewhere between 0 and 1. And you got to multiply that by this number here. This is, of all the planets that evolve civilizations, how many of those civilizations are around now? Remember, Earth, for most of its history, didn't have a civilization. Now it does, but how long will civilization last? We just learned agriculture 6,000 years ago. Or I guess I'm saying 8,000 now. All right. Maybe we'll be generous and say 10,000. 10,000 years ago, we learned how to plant. Already, 10,000 years later, that is nothing in geologic time. 10,000 years later, we have the power to destroy ourselves by multiple ways. We can do it with climate change. We're starting that. We're getting real good at climate change. We could also do it through nuclear weapons. One bad president, one mentally unstable president with his finger on the red button could kill everyone on this planet. We could kill everyone through pollution. We have several ways we could kill everyone after just 10,000 years. Are we going to survive? I hope so. I want us to survive, but how long will we survive? And in general, how long do civilizations last? What's the time frame between the time a civilization learns to plant crops and the time it kills itself? 10,000 years? 100,000? A million? Even if it's a million years, that's a tiny fraction of the lifetime of a planet. Could a civilization last 1 billion years? That would be nice. We simply don't know. So F now is the fraction of all civilizations that have ever existed and will exist in the future that are around right now. And we don't know what that fraction is. So, number of habitable planets just in our galaxy, I think I said millions before, it should be billions. Probably billions of Earth-like planets. Kepler spacecraft has told us at least that much. There are probably billions of Earth-like planets in our galaxy. Awesome. What is the fraction of those planets that have life? Well, okay, maybe that's pretty high. I mean, Earth had life very early on, and once life started on Earth, it was very tenacious. Even though we've had multiple extinction events, the complex life died, and the simple life survived and evolved into more complex life. This happens over and over again. Life gets more and more complex. There's an extinction event. Life becomes simple again, and then it evolves into more and more complex life yet again. So it might be that most Earth-like planets have simple life of some sort. Could be just single-celled organisms. So the fraction of life, the F life, could be 90%. And remember, to turn a percent into a fraction, you move the decimal to the left twice. So 90% as a decimal is 0.9. Okay, here's where we really don't know, though. What fraction of planets with life eventually go on to develop civilizations? I don't know. Could be 90%, 0.9. Could be 10%, 0.1. Could be 1%, 0.01. Don't know. And of all the civilizations, now let's go down here, of all the civilizations that have ever existed and will ever exist, how many are around right now? And that is closely linked to, can civilization survive long term? Once a civilization learns how to plant crops, and technology grows and grows and grows till they get to the point they can split the atom, they can affect their own climate and smoke themselves out of existence. They can increase the climate until increase the temperature of their planet until it's no longer habitable. We can do that. We're on the way to doing that. We're working on it. Just a few thousand years after they learn to plant crops, maybe they can split the atom and destroy each other with nuclear weapons. Maybe they can pollute themselves to where they can no longer grow crops or drink the water or breathe the air. There are several ways civilizations can kill themselves. How long in general do civilizations last? We don't know. So this fraction now, if civilizations do get through the growing pains and learn to survive long term, maybe humans will survive for 100,000 or 1,000,000 or 1,000,000,000 years. Maybe. If so, and if other civilizations do too, maybe this number, F now, is quite high. Maybe it's 50%, 0.5. Maybe it's something else. Maybe not. Maybe civilizations rise and fall very quickly, in which case F now would be very small. 0.01. 1%, or 0.001, a tenth of a percent. In which case, it might be unlikely that we're going to meet alien civilizations. So SETI, the Search for Extraterrestrial Intelligence, works by making the huge assumption that alien civilizations communicate the same way humans do, through radio waves. We communicate with radio waves for two reasons. Number one, our atmosphere is transparent to radio waves. You can send radio waves a long distance on Earth. You can't do that with infrared or ultraviolet, or most frequencies on the electromagnetic spectrum get absorbed by the atmosphere. Radio waves do not. Radio waves also bounce off the top of the atmosphere, off the ionosphere, so we can send radio signals even if we don't have a line of sight. So radio signals are really good for communicating, at least on Earth, and probably would be on other Earth-like planets. So the SETI astronomers assume that aliens communicate with radio waves. So they look at stars all around our galactic neighborhood, and they study those stars in radio waves to see if they can find communications, to see if they can find television shows or, I don't know, radio shows, something to indicate those aliens are communicating with radio the way we do. We even sent radio waves to distant stars. We sent a radio signal to the globular cluster M13, hoping that there would be perhaps an interstellar civilization there, because if there are planets that are able to host life in a globular cluster, it's not clear that there are, but if there are, that those civilizations would be more likely to jump from star to star to star because those stars are closer together. Of course, that also means those stars are throwing comets at each other, and so that might produce a lot of extinction events on those planets. We don't know. Oh, SETI at home. They shut it down. Sorry, I got to get rid of this slide. It used to be that you could hook your computer up to SETI and you could look for aliens. But no, that's not the case anymore. They shut it down. I'm so sad. All right, how many civilizations are there? I don't know. But the Drake equation is what we use to give us a mathematical framework for asking the question. You put in your guesses for each of those numbers, out pops a number. So what about interstellar travel? Is it hard? Yeah, it's hard. Are we ever going to do it? I'm saying probably not, but hopefully we can, maybe. I mean, it would be great if we could learn to go past the speed of light, if we could break the warp barrier. Remember, you cannot move through space faster than light, but space itself can move faster than light, and you might be able to ride that wave. Miguel Alcubierre in the 1990s found a solution to Einstein's equation that simply means a geometry of space-time that does not break the laws of physics, that would allow a starship to travel faster than light. However, the energy requirements are ridiculous. We don't have any idea how to produce that much energy. Plus, we would have to find some sort of exotic matter or some way to stretch space-time behind us. Matter with negative mass, which doesn't break the laws of physics, but also has never been observed in nature. So warp speed, traveling faster than light, doesn't break the laws of physics, but may not be possible. We just don't know. So let's put that out there as a possibility. Maybe in the future we'll find a way to go past light speed. Awesome, great, coolio, then we've colonized the galaxy. Although, if that's possible, why hasn't the galaxy been colonized? Our current spacecraft, Voyager, the most distant spacecraft from Earth are the Voyager probes. They have both just barely left our solar system. They haven't reached another solar system. In fact, they won't for thousands of years. I forget how many thousands. So they just left our solar system, and they're not going to reach another star for thousands or tens of thousands of years. So the Voyager probes are not likely to encounter any aliens. Just in case they do. Now, the odds are almost zero, but not quite, right? Who knows? Maybe there's some Vulcans out there who are monitoring us right now. We don't know. Just in case there are, the Voyager probes both have records on them. Golden records. Made of gold. Because, NASA has some gold laying around. Gold is resilient to the sun's radiation. That's why they use that. Gold is not going to be destroyed by the sun's radiation out in space. And it's a record, and it has images of humans, pictures of humans doing basic things like eating and drinking. It's got a map to Earth in case aliens want to invade us. that may or may not prove to be a wise idea. It's got instructions on how to build the record player, and the instructions don't use language or numbers. Right? There's no reason to think an alien would speak English or Spanish or Greek. What they do instead is use physical constants. They use binary numbers, zeros and ones. The map that they have is a map of pulsars. So they're assuming that it's a puzzle. If the alien civilization finds this probe and can solve this puzzle and say, aha, wait a minute, there are pulsars right here, and in the middle of those pulsars is our sun. Our sun is not a pulsar, it's just in between those pulsars. The Pioneer plaque has unsolicited nudes from Earth. There's a man and a woman, and again, this is a map with our sun right there. Each of these is a pulsar out here. And then once you get to our solar system, here is the sun, Mercury, Venus, Earth. So it tells them where to go. But again, current spacecraft are traveling at much, 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 much less than the speed of light, less than 1/10,000th the speed of light. So they're not going to reach another star system anytime soon. So if humans are going to go to another star system, unless we can find a way to build a warp drive, and again, that's science fiction at this point, though who knows, maybe in the future it won't be. Right now, we would have to deal with traveling less than the speed of light. Even if you could only approach light speed, it would still take 4 years to get to the nearest star. It would take years to get to the neighboring star systems. It would take energy, more energy than we know how to produce right now. Plus, if you approach the speed of light, you have to deal with time effects. As you approach the speed of light, time around you slows down. So if you were to somehow find a way to go near the speed of light and go visit Alpha Centauri, the next neighboring star system, Proxima Centauri, which is gravitationally bound to Alpha Centauri, is the neighboring star. It would take you 4 years to get there if you're almost traveling at the speed of light. 4 years to get back, and meanwhile, you're only 8 years older, right? But time around you slowed down, which means when you get back to Earth, although you have only aged 8 years, your friends and relatives on Earth will be dead. On Earth, centuries may have passed. You may arrive on Earth hundreds of years later, even though you only experienced 8 years. Because when you approach the speed of light, time does strange things. Time around you slows down. That seems like science fiction. It's not. That's well documented. We've measured that. So, also as you approach the speed of light, you have to deal with radiation. Even if you're not traveling at the speed of light, astronauts in our solar system have to deal with the sun's radiation. If you approach the speed of light, even radiation that won't normally harm you suddenly becomes very, very powerful. Powerful enough to put cracks in your ship. If they're micrometeors, the micrometeors will put cracks in your ship and the radiation will just burn you. So, yeah, that's hard. Another alternative that is, again, science fiction at this point would be an intergenerational ship. Maybe you have a ship that is completely self-contained. Generations of humans can live on it, and you send that ship to another star system knowing it will take thousands of years to get there. And you just assume that everyone on board knows they're not going to make it, their kids are not going to make it, but their great-great-great-great-great-great-great-grandkids will make it, assuming they survive, that the ship is able to support life that long. So as of now, the likelihood of visiting another star is remote. And moreover, a guy named Fermi offhandedly made the comment that later became known as Fermi's paradox, which is, where is everybody? If alien civilizations are really there, why haven't we seen them? I mean, if alien civilizations are there and can travel between the stars, if that is even possible, surely someone would have done it by now. And if someone had done it by now, we should have a united federation of planets already happened. I mean, our sun is a fairly new generation star. There were stars around long before our sun. Our sun is only 4.5 billion years old. Yet the galaxy is 13 billion years old. So by the time our sun even began, there should have been alien civilizations colonizing the entire galaxy, if that's possible. And some folks suggest, though it's not an airtight argument, that because the galaxy is not yet colonized, it must not be possible to colonize it. That's not an airtight argument. You could make a counter argument to that. There's got to be a first. It's just food for thought. So, what's the solution? Why have we not seen aliens? Well, it might be that alien civilizations are rare, that, yeah, they do exist, but that the nearest alien civilization is hundreds of light years away, so that we can't detect their radio signals. The radio signals get lost in the noise. Or it might be that we're it. Could be that we're the only one. I personally doubt that. But I don't know. That's the whole point of this lecture. So it's also possible that civilizations are common, but they're far away, and that there's simply no way for biological life to travel between the stars. No alien in our galaxy, at least, has figured it out yet, because maybe it's not possible. Or there's a darker solution. Humans have only been around for a few thousand years. Human civilization has only been around a few thousand years. We've only known how to grow crops for a few thousand years, 6 or 10,000. And already we have the ability to destroy ourselves. How long until we do? And how long do civilizations in general last? If civilizations in general only last 10 or 100,000 years, it might be that they just never developed the technology to travel between the stars because they kill themselves first. Let's hope that's not the answer. Or maybe aliens exist and we just haven't met them yet. Maybe there is a united federation of planets and they've seen Earth and they're like, y'all aren't ready yet. Yeah. They see us the way an adult sees a teenage party, maybe, and be like, yeah, y'all are having fun, but I don't want to be there when the cops get there, so y'all do your thing. Maybe that's the way aliens see Earth. I don't know. So, we're certainly not going to travel between the stars anytime soon. Are there aliens? Maybe. If so, where are they? We don't know. It's possible that simple life is very, very common. In fact, I suspect that's the case, though we've only found life here on Earth. How common are civilizations in the galaxy or in the universe? That we simply don't know. They could be very common, and we just haven't found them yet. Or they could be not very common. Is it possible for civilizations to travel between the stars? There are plausible arguments to suggest that if it were common, it would have happened already. But again, maybe it has happened, and the aliens just don't want to talk to us. Well, that was fun. I hope that you take from this lecture a good thought. I hope you think a lot about whether aliens exist and come up with an opinion that is flexible. Your opinion on aliens should be rooted in our collective ignorance, because for everything we know, there's a lot more that we don't. So let's end as we usually do. And this is the last poem we're going to do. So do it with me. This is the last chance. Say it with me. We'd sure like to know, where'd the aliens go? If you see them, please tell them, say hi to us. But please, don't conquer us. When I say astronomy, you say rocks. Astronomy! Did you say it? Yeah, you did. Here's a summary slide, and here's another one.